So this talk is, as the title suggests, mainly going to be about epitaxial growths. Now, if you think of any end-to-end technology, and you have heard so many speakers from this morning, you need some simulation guidance, first of all, to tell you what you need to grow, what should be the ideal composition, thickness, and all that. Then people like us should come in and try to grow structures based on that. People with material characterization expertise should come in and tell how good our structures are. You have heard the previous speaker, how difficult it is to actually optimize and make devices, the lithography steps, and someone needs to come in to test those devices. If the end product, that is the device, does not work, you need to rethink your whole strategy. So there are multiple components for an end-to-end technology: simulations, epitaxy, characterization, lithography, and device processing and device optimization. So difficult as it is to cover everything, I just thought of, let me just take up one area, that is epitaxy, and try to go deep. So what is epitaxy? The first speaker for today covered it extensively, but nonetheless, let me go ahead. So it's a very special form of thin film deposition. Now, people who have worked in nanofabrications, if you do a spin coating, a photoresist, that's also a type of thin film deposition, right? You are depositing something on top of something, but that's not epitaxy. Epitaxy is where there is a strict, like a crystallographic relation with the substrate that you are growing on. So by and large, there are two different methodologies we follow. So there is one bunch of techniques that rely entirely on physical processes. An example of that would be an MBE. So here, let's say if we are trying to grow silicon germanium, we would send in flux of silicon atoms, flux of germanium atoms. These would undergo some physical processes like diffusion, nucleation, adsorption, desorption, and eventually, if conditions are correct, they'll give rise to an epitaxial silicon germanium film. On the other hand, there are techniques which rely on chemistry, chemical processes. So an example of that would be CVD, chemical vapor deposition. So here, to grow silicon germanium, we would send in a silane molecule that would undergo a series of chemical reactions on the surface and give us silicon atom. Germane would undergo the series of reaction, give a germanium atom, and then they would undergo this physical process. Again, diffusion, nucleation, desorption, and give rise to your film. Epitaxy is often tool agnostic. Like we often show these pictures, it gives a feeling that these are the only two tools where you can do epitaxial growth. If conditions are correct, you can do it through sputtering, laser deposition, so on and so forth. So one question is, why would an atom, if we think about the fundamentals, why would an atom even leave, let's say, the vapor environment and get incorporated into the solid? So the reason for that is as follows. Let's say silane, it has to break the silicon hydrogen bonds, it costs some energy, but then when it can go inside a solid and form these strong covalent bonds, the heat of enthalpy that's released, the energy gain is much more from that. So that is one driving force which is measured in terms of the chemical potential of the atom in the solid and the chemical potential in the gas. So the chemical potential in the solid is defined by a bunch of parameters which you can group together as the molar Gibbs free energy. It is usually defined at standard temperatures and pressure. 1 atmosphere, 273 degree Kelvin. For all solids, this is tabulated. You have a data sheet. Now, under growth conditions, we are at a different, we are different from the standard conditions, but the molar Gibbs free energy does not change that much. So this part we can roughly take to be a constant. What we epitaxy engineers can really play with is the chemical potential of the gas phase. We are the one choosing the growth temperature. We are the one choosing the partial pressure inside the chamber. We are the one playing with this difference, delta mu. If this difference is large, there is a natural driving force. We call it supersaturation. So we play with the supersaturation during growth. An atom on the surface, it's metastable. It has to go inside and form bonds to be stable. So an atom on the surface, it undergoes, let's say, 2D random walk. It's a kinetic process, temperature dependent. Diffusion energy is of the order of 1 electron volt. The time scales are of the order of few tenths of nanoseconds. Within, let's say, if it's making random walks or if it's making hops, it has to find a proper site where it can attach a nuclei. If not, I told you it's metastable. It will simply dissolve back. The desorption energy is of the order of 3 to 4 electron volts. The time scales are of the order of milli to microseconds. So an atom gets multiple chances to hop and find the nucleation site. If it cannot, it simply will dissolve. So the diffusion length on the surface is square root of the diffusivity times its dwell time. The dwell time is the time it takes to dissolve. This for CVD systems is like 10 to 50 nanometers. For MB systems, it's an order of magnitude higher. So let's say with these random walks, what it happens is a group of atoms can come together and form something called a critical nucleus. Now, to form a critical nucleus, there is an energy cost that it needs to pay. Why? Because when atoms are coalescing, the bulk contribution to free energy goes down. Let's say it's a 2D nucleus, but you are creating a new edge, a periphery. You have to pay that energy cost. So this energy cost is, again, you see, it depends on the supersaturation which we get to choose or you get to play with. Critical nucleus is that size beyond which the growth of these islands becomes thermodynamically favorable. That too depends on delta mu. So the situation is somewhat like this. You can see that a group atoms are hovering on the surface, few small nuclei kind of dissociate. They are not energetically favorable to grow, but really which crosses the critical nucleus size kind of coalesce and try to form a thin film. This is like classical nucleation and growth. This picture is more or less ideal for, let's say, most conventional growth conditions. Sometimes when we are at really low temperature, extreme conditions and very high supersaturation, what happens is the atoms which land on top of these islands, they do not have enough energy like to trickle down and kind of attach to a growing island. So they kind of stick to where they land. This creates a rough texture, we call it kinetic roughening. This is something we generally try to avoid while thin film growth. So you see how critical are these growth parameters that we get to choose, T and delta mu. It's tuning your potential barrier, it's tuning your critical nucleus size, it's tuning the morphology and the texture of the film. So these are the things we get to control. There is another growth mode, which is called step propagation. So this happens, every surface has a steps. If you can see it in AFM, the reason is, let's say you are cutting a silicon ingot. If you cut exactly along a crystallographic plane, you will never have steps. But our cutting machines that usually have an offset of 0.1, 0.2 degree. So when you cut with an offset, you create these atomic steps and terraces. Sometimes we do cut deliberately, we call it miscut, 3 degrees, 4 degrees, 5 degrees to induce a lot of these steps. So an atom on the surface, if it's difficult to form a critical nucleus because, let's say, of low supersaturation, it can simply diffuse and add to and attach to a step. There is no barrier to attach to a step. It can simply attach and a step kind of propagates. Now, I don't have a very good picture, but this is kind of an in situ SEM from MBE talking about showing you the growth of, you can see how the steps are moving. So those atoms are attaching to a step and the steps are propagating one after the other. So if this is taking place on the entire surface, you have a layer growth as well. So now let's come to heteroepitaxy. And to do that, our first speaker did introduce this concept, but let me just revisit that. We have to think about surface energies. We have a substrate. We have a surface of the substrate with air. Now we are creating a new material on top of it. So we are creating a new surface, that of the epilayer with air, and there is an interface with the substrate and epilayer. So this is the new surface, that is the interface. So if this new surface energy configuration is kind of smaller than the previous one, this is where a film wets the surface, like water kind of spreading and wetting a surface. This is conducive for 2D layer by layer growth. If this new surface energy configuration is larger, generally the film tries to minimize this interface area between film, the substrate and the epilayer. And it does that by forming these islands, just like water tries to form droplet on some other surfaces. This is called 3D island or Volmer-Weber. There is a third mode, Stransky-Krasnov, which starts off in this configuration. The surface energies are conducive for film growth. It starts layer by layer, but because it's heteroepitaxy, the lattice constants are different, and strain might build up in these layers, and it's strain which kind of switches the growth from 2D to 3D. So it kind of forms these pyramids and huts. Why? Because when you have such free surfaces, these can radially relax and release whatever lattice strain has been building up. This is not possible for a thin film like this. You have to have these truncated facets which can simply radially relax. This is a way in which the system tries to lower the surface energy contribution to total energy, which is why it's forming these 3D islands. This is a case where the system tries to lower the strain energy contribution to total energy, which forms these faceted islands and so on. So speaking of strain, so let's say this is your substrate silicon on which you are growing an epilayer. It has a larger lattice constant. Because it's epitaxial, you need to form these covalent bonds. You can see that in this direction, the lattice is compressed because it has a larger lattice constant. On the free side, the lattice is stretched. This is called tetragonal distortion. So when you do an XRD, you actually measure this out of plane lattice parameter. And using the elastic constant, you can get an idea of the in-plane lattice parameter. When you compare it to the bulk lattice parameter, you get an idea of the misfit. The misfit is what determines the strain in the lattice. So the strain energy scales with proportional to height. So the thicker it grows, the more strain energy that it is accommodating. And at some point, if the strain energy is too much, the crystal thinks, okay, let me release some of that energy by breaking an array of bonds, which is what is called a dislocation. You can see that even in TEM. So you can see that a half plane is introduced there, just like you have a half plane here. Now, what is that thickness? There are different models. None of these models are very accurate. One is a force balance model, one is an energy balance model. These more or less gives the upper and lower limit. Experimental data usually lies between these two. One critical parameter you see in all these models is this parameter B called the Burgess vector. It's a crystallographic parameter, so you have to start drawing a contour that surrounds the dislocation. Let's say you start from here. You go 1, 2, 3, 4 steps to the right. 1, 2, 3, 4 down. You come back 4, then you go up 4. You see that because now you have a dislocation, you are no longer able to close this loop. So this extra crystallographic vector that you need to close this contour is what is called the Burgess vector. In this configuration, you can see that the dislocation is inside the plane and the Burgess vector is kind of perpendicular to it. This is what we call like an edge dislocation. One cool way of determining this, if you do a geometric phase analysis, you can do that through TEM, and from high resolution TEM data, you can see the dilation and the rotation of the lattice. Because you have an extra half plane there, on top of the dislocation, the lattice is squeezed, and below the dislocation, it's kind of stretched. So you kind of see a dipole-like strain distribution, which is a hallmark of, let's say, an edge dislocation. Now, a lattice can be subjected to even shearing stress, and a natural response to that is screw dislocations, something like this, where the Burgess vector is parallel to the dislocation line. It adds an extra half step on the surface. So if you see it from the top view, TEM or AFM, you will see like these spiral-like structures, which is easy to tell that that's a screw dislocation. But unlike the edge one, imaging the dislocation core in TEM is not that easy. I mean, you need special techniques. So I don't want to go into it. If you are interested, you can read these papers. You need convergent beam electron diffraction techniques to actually see, because in normal, the displacement of atoms are parallel to the electron beam. The G dot B is 0, and you cannot actually image a screw dislocation like that, unlike an edge dislocation. But for the systems I'm going to talk about next, Group 4 systems, silicon, silicon, germanium, we see a plenty of mixed dislocations. You see this marked by 60 degrees. That means the Burgess vector is making an angle of 60 degree with the dislocation line. These have partial screw nature, partial edge nature, and they will play an important role as to how we do a post-growth preparation of these samples. Okay, so this was like the basics of epitaxy. I was told that there will be plenty of PhD students from diverse backgrounds, so I just took classic epitaxy theory and kind of lay it on to you. Sorry to the experts in this room, they are probably seeing this for the billionth time, but I thought this was important for the diverse set of students community. So this is the summary so far. So epitaxy is a special form of thin film deposition where a crystallographic order is maintained. So growth is driven, the driving force is kind of the lowering of free energy of the system when an atom goes from a vapor phase and forms solid or strong covalent bonds in a solid phase. So an atom is a metastable on the surface. It needs to diffuse and find a nucleation site, or else it dissolves. We discussed two growth modes or growth morphologies. One is the classical nucleation and coalescence, and the other is the step propagation. We discussed about the three growth modes, the 2D layer by layer, the Volmer-Weber, the Stransky-Krasnov. The Stransky-Krasnov is a special one. It's kind of a mixture of 2D and 3D. And we discussed about strain and misfit and edge dislocations. And in heteroepitaxial systems, in group 4 ones, it's important to remember that we have a lot of mixed dislocations, which are both edge and screw in nature. So let me go quickly over to some of the use cases that is relevant for this workshop and this community. So just a bit about my background. So in my PhD, I was working mainly with UHV CVD systems, and I was using isotopically enriched precursors. These precursors are now in very high demand for, let's say, growing silicon-based or germanium-based quantum materials. But back then, we still did not have the expertise to grow such quantum materials. And what we did was grow silicon nanowires. Now, when we play with isotopic mass, you affect the vibrational properties and phonon behaviors, and that's what we studied. Mainly, that was the topic of my PhD. So this led to this nice publications. We also started building a small 4-inch CVD reactor. It was supplied by Plasmonic Canada. So we are growing germanium on silicon, germanium tin. This again led to a nice bunch of publications. I worked on home-built MOCVDs, growing arsenides and phosphides. Not much, but the experience is there, and this too led to some nice publications down there. In my first postdoc with applied materials, I got the opportunity to work on their 12-inch 300 millimeter Epicentura CVD systems, growing silicon germanium heterostructures. And later in Leibniz Institute, Germany, I had worked with thermal and plasma ALD tools, growing transition metal dichalcogenides and their multilayers, all on silicon dioxides. Again, some good publications down there. So obviously, I cannot talk about all of them. You can see that even in the CVD world itself, there are so many different forms of CVD. Down there you have UHV CVD. This is, you can think of the conditions to be analogous to MBE, ultra high vacuum conditions. It gives very good crystallinity, excellent uniformity, monolayer control, chemical purity is excellent, but you can put, let's say, 1 4-inch wafer at max. Batch processing is almost negligible. Throughput is very low. On the other hand, you have atmospheric pressure CVD. As the name suggests, it works in the atmospheric pressure. Very fast growth rates. Compare the growth rates there and there. You can put 8-inch, 12-inch wafer, but batch processing is still limited. The main problem is the chemical purity. Because of the high pressure, sometimes precursors react in the gas phase. You want them to react on the chemical reactions to take place on the surface. It reacts on the gas phase, forms particles in the vapor phase, which drops down on your film and contaminates. So the chemical purity is a big issue there. In the middle, you have these two, LPCVD and RPCVD. You get good enough crystal quality, good uniformity, purity. The best part is the extremely high growth rates. You can process multiple 12-inch wafers, which gives excellent throughput. And industry cares about throughput a lot. It's the number of wafers processed over processing time. And when industry calculates all the semiconductor industries, its economics, the cost per wafer is the tool capex, processing opex over throughput. These two are like the workhorse of the semiconductor industry. This is a FEOL called the front end of the line process when you are doing blanket epitaxy on a blanket wafer. And then when you form these trenches and you need to deposit oxides and nitrides to isolate or to passivate, this is usually the tool, LPCVD. Batch processing is possible. So let me go into some of the structures. So as a student, what we or my supervisor told me, first try silicon on silicon. Why? It's easiest. You don't have to care about surface energy. You're drawing silicon on silicon. You don't have to care about strain. It's silicon on silicon. But it gives a very good feel, a hang of the system that we are trying to do. It's one of the easiest things to grow. It also gives an opportunity to refine your cleaning steps. Often what we do in academia is we degrease with acetone and isopropanol, and then we just do an HF dip and anneal and we clean. It cleans all right. You can see that you have grown crystalline silicon on top, but you can still make out where is the interface. That means your cleaning is not perfect. You still have some organic residues and metallic residues. A better cleaning process is called an RCA cleaning. This is kind of standard in the industry. There are some standard clean solutions 1 and 2, and you just follow these steps. You can see that you no longer make out where is the interface. It's absolutely clean. So this gives a kind of a good hang on things. Next, we targeted that was not so easy, germanium on silicon. Germanium on silicon wants to grow in this Stransky-Krasnov mode, the one that I told you. You can see how these growth process, first it nucleates these islands, then these islands grow in size, and finally these islands coalesce. And if you look at it from the cross-sectional view, it looks horrible. All these islands, faceted islands, when they merge, they create stacking faults. These stacking faults kind of split into a partial dislocation. So it's a mess there. It's utterly rough. There is not much you can do with it. What we create a condition is, how can we stop these islands from nucleating? First, in CVD, let's say after annealing, we lower the temperature to about 300. We grow a layer in very high flux of hydrogen. Where is the hydrogen flux? 5 to 6 standard liters per minute in very high pressure. We have seen that in this condition, island nucleation is kind of stopped. The film still tries to grow in a layer by layer fashion. So we have stopped this 3D island nucleation. The misfit strain is still building up. Remember, these islands nucleate to relieve the misfit strain. The misfit strain is building up, and when it crosses like 4 to 5 nanometers, that strain is released to nucleation of dislocations. Dislocations are something we can still work with, we can still live with them, but not this. This is something you cannot live with. Once this seed layer is grown, we are confident that it will keep growing in this layer by layer fashion. So we dump up the temperature, you get a faster growth rate. So there you can grow 2, 3, 4 microns of germanium. These lines, what you see, are dislocations propagating. Finally, we heal the crystal using cyclic annealing, and I'll tell you why cyclic annealing is necessary. It kind of gets rid of these dislocations that were formed. Now, I told you about mixed dislocations. Remember, if it is a pure edge dislocation, a lomer dislocation, if this is the interface, its glide plane and slip plane is this interface. It never propagates upward. It releases the strain and it remains in this interface plane. These mixed dislocations, because they have a screw nature, they nucleate differently. They nucleate on a growth front as half loops. You can see these loops there. So what it happens is it selects closed packed plane. For this system, it's the 111 plane with the highest atomic density, and it glides down this 111 plane, and once it reaches the interface, it forms this misfit segment. It's only this segment down there, this in-plane segment, that releases the strain. These threading arms are just a nuisance. They don't release any misfit strain, they just create helical distortion of the lattice. Now, why do we need cyclic annealing? I mean, why did we kind of anneal at high temperature, low temperature, high temperature, low temperature, because these threading arms, they can glide along this 111 plane. When they glide, so when we do this cyclic annealing, the lattice kind of periodically expands and contracts like this. This promotes the glide of this threading dislocation. So if they meet another threading dislocation with opposite Burgess vector, they kind of pairwise cancel each other. They can also meet another on a cross plane and pairwise cancel each other. Or they can move out to the edge of the crystal and kind of disappear. So you see that the crystal has healed so much after this cyclic annealing. Now, just because we don't see a dislocation does not mean that it's dislocation free. No heteroepitaxial system is dislocation free. It just has gone down the special resolution of TEM, which is 10 to the power 7 per centimeter square threading dislocation density. A better way is to see from the top view. So we have this chemical. So if you etch it, this typically etches germanium. The dislocations just etches faster than the film. So when you etch it from the top, you see these pits, and each of these pits is an arm of that threading dislocation. So when you count these pits, you can see before and after annealing, we got about 2 orders of magnitude improvement in the threading dislocation density. Also, we found that when you do this kind of cyclic annealing, the surface roughness kind of improves. And it improves better than we have tried constant temperature annealing. The cyclic annealing works better as far as the roughness is concerned. So cyclic annealing is a better technique to grow this high quality germanium on silicon. So once the germanium is grown, let's say what do we do with it? One of the materials that we grow on top is germanium tin. Now, I won't spend too much time on this. We have a speaker, the last speaker for today, Isama. His group is very active, and I hope he covers some of the topics. So germanium is an indirect band gap material. L value is lower than the tau value. If you start alloying with tin, germanium tin, you start pulling down both the values. It's just that the tau value is pulled down faster. You can see the graph here, how the L value and tau value evolves. That means for certain alloy composition, this germanium tin alloy will become direct band gap semiconductor. So in unstrained or relaxed germanium tin, this happens at around 8% tin. If you are growing under compression, you need a slightly higher tin, around 10%. If you grow under tension, you need slightly lesser tin. This crossover band gap is strategically very important. It starts from around 2 micron, and the more tin you add, the band gap shrinks. It can go to 2.5, 3, 4.5, so it's covering the shortwave infrared, mid-infrared region of the electromagnetic spectrum. Why is it important? For the silicon photonics community, we have all these passive components on silicon, on SOI. What was missing so far are lasers, photodetectors, and your active components. Now you have all group 4 elements with the possibility of making lasers, LEDs, photodetectors, monolithically integrate them on silicon using CMOS compatible processes. You don't need a new fab for this. So this is opening up the entire market for silicon photonics industry. The problem is, however, this is highly metastable non-equilibrium alloy. So the phase diagram, if you see, of germanium and tin, it says that at max you can add 1% tin in germanium lattice. At max. And here you need around 8%, 10%, so 1 order of magnitude higher than the solid solubility limit. So think of this. An equivalent picture is this. Let's say I give you a jar of water and I tell you, you can at best dissolve 1 spoon of sugar in it. That's the solid solubility, max. Now I tell you, give me a solution that has 10 spoons of sugar. What will you do? You'll heat it up. You'll add more sugar, stir it, try to dissolve it. But what happens when it starts cooling down? It takes few sugar molecules to form a critical nucleus. Everything crystallizes back, phase separation. So if we don't do things properly, this is what we end up with, a messed up structure. Complete segregation of tin on the surface, bulk precipitate formation. There is not much we can do with it. So how do we tackle this using epitaxy? Again, not going in details, there are 3 main control knobs. See, for this germanium tin growth, we need to keep a very high gas phase ratio of germane to tin. This is needed because tin chloride needs excess germanium to crack this precursor. That also means that there is not much tunability we get through precursor flux. See, at any temperature, you start from a composition, you start increasing the tin flux. At some point, there is so much tin at the surface that it starts to segregate. And it's end of epitaxy there. Rather, you see that temperature is a better control knob. So when you lower the temperature, keeping the flux the same, you suddenly start increasing the tin content. Why? Because of these lot of kinetic processes that take place on the surface. When you lower the temperature, a lot of these competing kinetic process slows down, making it easier for tin to get incorporated. That's the best I can say at the moment. So lower the temperature, at the same flux, you get higher tin content. The other is often what we see in heteroepitaxial systems is spontaneous relaxation. So see, when we grow germanium tin on top of germanium, it has a larger lattice constant. So initially it is very highly compressed, or there is a high degree of compressive strain. Tin is a larger atom compared to germanium. So when things are already very compressed, it finds it difficult to make its way into the lattice. When you start growing thicker, the moment dislocation starts to nucleate, the lattice starts relaxing. The moment it starts relaxing, this big tin atom finds it's easier to get inside and kind of nucleate. So this is what you see here. Here you start, this is a concentration profile. So you see that here we fix the temperature and the flow. Let's say we have 10%, and then we don't touch the temperature, we don't touch the precursor flux. We just let the layer grow thicker and thicker, and you see suddenly the tin concentration starts to increase. Naturally, we don't do anything to it. It's simply because the lattice has started relaxing. First, it grows rapidly. Then when the lattice is close to being fully relaxed, it slows down. Once it's fully relaxed, it kind of flattens. This is a classic case of spontaneous relaxation enhancement that we see in this. So based on these strategies, we grew different kinds of germanium tin layers. So we start with a nominal flow of 8%, and then we don't touch the precursor flux. We lower the temperature, there is a jump in tin content. Then there is SRE. We lower the temperature once again, there is a jump in tin content. So we get around 17, 18, 20%, 20 times higher than the solid solubility limit. So if we follow this strategy, you can get wafers which come out of the CVD like this, mirror-like shine. You know, this is monocrystalline, grown perfectly. If you try to grow a 17% layer with one shot, this is what you will end up with. Braided, milky, things have segregated, and this is not good. So this layer, you see, it's emitting at around 3.4, 3.5 microns. And the band gap, we know, is a function not just of composition and strain. There is some residual strain in this top layer. So when you form this microdisc, by under etching the germanium, you release that whatever residual strain was there. You can see that in the Raman spectra as well. You can see how when you release the strain, the band gap changes. You can see in PL as well. It's shifting towards longer wavelength, 4 microns. If you're able to put a layer of silicon nitride and induce tensile strain, you can put it even deeper towards 5 microns. You're covering entire shortwave infrared to mid-infrared bands by simply playing with composition and strain. So I'll not go into details of the devices. As I said, these are silicon compatible photodetectors. Again, I would hope the last speaker covers all this today. His group is very active in this. Nanowire based lasers, these are optically pumped. The Arkansas group is another group which is very active in this. Germanium tin based electrically injected laser, everything is on silicon. It's working up to 145K because these materials still needs to be optimized in terms of point defects, extended defects, LEDs. So all photonic and optoelectronic components you can think of growing, once these are optimized, directly on top of silicon without needing any wafer bonding or any other heterogeneous integration. So as I said, I'll not speak about devices so much, but let me move over to some structures that I think are more relevant for this workshop. This is the project that I was doing with Applied Materials. The motivation was not quantum application as such, but it's close. You see that our modern microelectronic industry, your laptops, smartphones are all driven by something called FinFETs. We made a transition from planar MOS to FinFET to better electrostatic control. We know when channel length shrinks, we have all these short channel effects. And here, the Oxide is covering the gate is covering the channel on all three sides. It was seen that when things go below 7 nanometer node, even FinFETs would start having problems. You need gate on all four sides. This is called a gate all-around transistors. This is what Samsung is doing for its MCBs and DRAMs and everything. So the starting epitaxial layers are something like this: silicon germanium with 30% germanium. Then you have to selectively etch the CG layers. I will talk only about epitaxy in this talk, but just to give you a feel, there are multiple papers available as to how to do this fabrication steps. It's a detailed fabrication covering 30 or 40 steps. If you are wondering how do you selectively etch CG, that too we have both dry etch and wet etch. You can see with only 25% germanium you get etch selectivity. Dry etch kind of performs better. It kind of gives you a kind of a square type profile. But these methods exist. Let me not go into fabrication so much. Let me come back to epitaxy. So what was it we were finding it so hard? So when growing this on silicon, we saw that the transition from silicon to silicon germanium is okay, rather smooth. But CG to silicon transition is not okay. The reason that we found after a lot of investigation is when we switch off, let's say, germanium here. So we have grown the CG layer and we want to go to silicon, we switch off germanium. These germanium atoms make a thermally activated jump from a subsurface layer to the surface, and they kind of cluster. And this is a kinetic process. So this is more dominant when we start growing layers at high temperature. And we needed high temperature for better crystalline quality. So how do we go from an interface that looks like this, wavy and kind of segregated, to a crisp and clean interface like this, silicon to silicon germanium, both the forward and reverse? That was kind of the challenge we were thinking. So I'll show you what industry calls process optimization. And these are some of the steps we followed. What we mainly learned is a little bit of chlorine in the chamber helps. Why? Because chlorine passivates a silicon surface much better till much higher temperature than hydrogen can. What are the effects? First of all, you see chlorine is a natural etchant for germanium. So it's kind of grow, etch, much like the accelerator and brake for your car, right? There is like two counterbalancing forces. One is that. The next you see, let's take this curve. So we are increasing the germanium flux, and here are the graphs for different concentrations of HCl. So how did we introduce chlorine? I forgot to say that. So we've switched from disilane to a precursor called dichlorosilane that has two chlorine atoms. And we also introduced deliberately some HCl gas into the chamber. So what happens? So you see atoms, it needs free sites, open sites to incorporate a nucleate. When majority of these sites are being occupied by chlorine, chlorine doesn't want to dissolve, the growth of a monolayer takes that much longer. Which is why you see with increasing chlorine concentration, HCl concentration, the growth rate simply falls. This is one observation. When you bump up the temperature from 750 to let's say 850, a lot of chlorine starts dissolving now. So the growth rates are a little higher. So for, let's say for this red one, you start from somewhere around 12. There it's a little higher. For the red one, you start somewhere around 17. So the growth rate starts bumping up. The another thing you see is what is happening to germanium concentration. You see, as we increase the chlorine flux, the HCl flux, the germanium concentration is kind of increasing. Why is that? Because chlorine loves silicon. They form this volatile chlorosilane. Chlorine doesn't want to dissolve alone, but the moment it meets silicon, it dissolves as volatile chlorosilane. So the competition for germanium is decreasing. That's why even at a same, let's say, germane flux, when we increase the HCl flow, we see that the kind of the germanium concentration is increasing. But most important is this thing. Because chlorine sticks to the surface, it stops this subsurface exchange process. This was the main culprit where we were having a graded interface. So with hydrides, you see that around 550 degrees Celsius, you have a sharp interface. That's okay. The moment we go to 700, the hydrogen dissolves and you have this germanium moving on to the surface and segregating. You get kind of a graded interface. We come to the chlorine environment now. With 800, even at 900, we found a really sharp interface, this one. At 1000, however, 1000 degrees Celsius, even at the chlorine starts dissolving. And that's where you start seeing these segregation effects again. So you see, we could grow very high crystalline quality up to 800, 900 degrees Celsius with really sharp interfaces. So you could grow 3 periods, 6 periods, 12 periods. And this is the strategy that you need for some of the materials that Professor Sudo showed in the previous slide. You need 30% germanium, silicon germanium with a silicon quantum well, very high crystalline quality, very sharp interfaces. We could grow 12, 16 of them. You need one of them to be able to kind of build your structures and form your spin qubits. So you can read more about that in these ACS and this nanoletters paper. Let me not go into it. This is a different study, but this is how you optimize a structure. Things were not as you expected. You wanted sharp interfaces. You saw one of the interface was problem. You understand what's happening at the surface. You try to come up with a more optimized recipe. And this is what is called process engineering by an industry. So you go from an unoptimized structure. 5 minutes? Okay. So I'll show you quickly another structure that I work with. Again, very important for this workshop, for this community. Germanium, silicon germanium, QCLs, quantum cascade lasers. These are for terahertz application. There is a wide variety of applications for terahertz. Unfortunately, terahertz is a region, let's say, where both electronic and photonic devices kind of are not very effective. That's why we call it a terahertz gap. India has its own terahertz roadmap, but to make compact integrated terahertz devices, you first need to come up with terahertz sources and detectors. It is currently being served by gas-algas structures grown on gallium arsenide in MOCVD. So it has an injector level that pumps electron into an upper lasing level. The electron makes a downward radiative transition. This releases a terahertz photon. And this lower lasing level, it has to quickly depopulate. So this is aligned to an extractor level. And this extractor is kind of tunnel coupled because of when you apply a bias, the bands bend. These is tunnel coupled to the injector of the next state. So very quickly, this is what it is. So a single electron can emit a photon, go to the next state, emit a photon. So the gain of this is theoretically supposed to be very high. The problem with gas-algas is this is polar semiconductor. The lifetime of an electron in that upper lasing level is determined by electron phonon scattering. That's why gas-algas QCLs, it's very hard to make them operate at room temperatures. They are usually Peltier cooled. We tried a structure for this Flash European project based on germanium, silicon germanium QCLs. You start with silicon, grow the germanium layer like the one I showed you. Then you slowly grade the composition down to about 85% germanium. This forms your buffer, and then you grow the kind of the multi-quantum wells. So these are the growth parameters. Why group 4? Remember, these are inter-subband transitions. You really don't care whether the material is direct band, indirect band. It's not from conduction band to valence band. This is intraband. The lifetime of an electron in non-polar semiconductors like silicon germanium is mainly determined by interface roughness scattering, not through phonon. So in principle, you can make them work at room temperatures. So if you have a structure like that, you can see the interface and all that, but how do you get the roughness? For calculating roughness, you need to see something like how the interface looks like. TM does not give you an interface roughness. So since I don't have time, I'll just quickly skip over this. We do a technique called atom probe tomography. So very quickly, atom probe tomography is based on electric field induced evaporation of atoms. You start from a needle-like specimen, you make that through fib, you apply a bias and a pulsed laser at the same time, and atoms fly up from this tip, one after the other. And then there is a detector, a position sensitive detector. It records the X and Y coordinate of where the atom came from. The Z coordinate is synchronized with the pulse, and all that is happening in a time of flight mass spectrometer, which records its chemical identity. So these are the four essential things you need to kind of reconstruct in an atom by atom fashion your original sample. The X, Y, Z coordinate and what type of chemical identity is. So this is a reconstruction, so you can see data sets like this. So here is like a GAN in-GAN kind of multi-quantum well. You can see where the dopants are. It's a 3D atomic view, and from such views you can see we can kind of reconstruct the interface plane. This is not possible with any other technique with such high spatial resolution. This is an interface between the quantum well and the barrier. On this interface you can run a wide variety of statistics. For example, we have run the roughness power spectrum. You fit it with a Gaussian. You get what is the RMS roughness of a buried interface. What's the roughness correlation length of a buried interface? If there is any vertical correlation of these buried interfaces. And based on that, we run some models as to what is the interface roughness scattering, what is the maximum gain that is possible. So what we found is their structures did have some problems. So there were some parasitic coupling between the injector state and not with the upper lasing level but with this parasitic level. So the group kind of came up with a more optimized design. This is the latest work. I was not part of this study. To form these parabolic quantum wells where the germanium concentration is varying parabolically. Here you have a better control over the mini bands which mimics that of a quantum harmonic oscillator. With this, if you take a typical loss line, you see that germanium, silicon, germanium at room temperature can outperform gas-al-gas structures as well. So here is the last structure I'll show you. So germanium on silicon germanium, germanium is compressively strained that lifts the degeneracy at the valence band. The heavy holes are your whole ground state. Here is a structure grown on silicon, germanium, then germanium tin. Remember, germanium tin has a larger lattice compared to germanium. When you grow a germanium quantum well now, it's tensile strain. Now the light holes are your whole ground state. Light holes have some interesting properties that needs to be systematically investigated. And it was investigated in this advanced materials paper. I was just talking about the epitaxy. So in this talk, I tried to bring home to you some of these heterostructures that are very relevant to the quantum computing and the spin quantum computing community. So you have to start with germanium growth on silicon, 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 germanium heterostructures, germanium, silicon, germanium heterostructures, germanium, germanium tin heterostructures, all grown epitaxially on silicon through RPCVD. So before I conclude, there is a bit of a small advertisement. There is a postdoc opportunity. So it's lithium niobate based photonic integrated circuits. The work location will be shared between my institute and IIT Kharagpur. These are desirable skills, any deposition tools, characterization. If you are good with FPDT, optoelectronic testing, interested candidate, please send your CV. This is a very interesting project you'll get to work on. So I'll end with this little advertisement. This is not a summary, but kind of the philosophy that I learned over the years through epitaxy. Often we think that while doing growth, composition and thickness is the critical things we have to tune, but these are some of the easier things in epitaxy, tuning composition and tuning thicknesses. It's mainly a fight between thermodynamic driving forces, which tells a system which way to evolve to go to the minimum energy configuration, and kinetics, which tells a system how fast you can evolve. And sometimes using kinetics, we can cheat thermodynamics, like we did for germanium tin, like we stopped those Stransky-Krasnov islands from forming, like we stopped from germanium to segregate in silicon, silicon, germanium. It's always a fight between thermodynamics and kinetics. Heteroepitaxy, we have to live with defects. We cannot have defect free. It's just depending on final application, what is the tolerable limit of defects and how we can manage defects. Strain and surface energy in heteroepitaxy becomes critical. Understanding them is the key to have more optimized layers. And the devil lies in the surface. The surface is the killing factor. If we don't optimize the surface, if we mess up the surface, that thing will simply be repeated layer after layer, layer after layer, and we'll get a crappy material. So everything that has to do with epitaxy is to understand the surface. We understand the surface, we can create reproducible epitaxial parameters for growth. With that, I end my talk. If there are questions, I'd like to take them.
Okay. Thank you. It was very much wonderful, sort of refreshing and educating for us. I think thanks for sort of presenting. It's a very important topic. So, question.
You mentioned the cyclic annealing process. So, is there any calculation related to cyclic annealing? How delta should be? How much cycle should be?
It's more trial and error. We have an idea, but if you want a formula that what should be delta T and the it's trial and error.
And other question is, if two different material for heteroepitaxy, one is very thermally stable material and other one is high thermal expansion, how to deal with this property for heteroepitaxy?
So if there is their thermal expansion coefficient are widely varying, when you heat up the material and cool down, they will cool down at different rates. That often creates cracks on the surface. So very high degree of thermal mismatch is always a problem. So if one cools down, let's say 3 times faster than the other, you will shrink one so much that you can see actually cracks appearing on the surface due to surface stress. Well, there is no real solution for that. You have to quench down. So those are the kind of material systems that we would generally avoid with very high degree of thermal mismatch. Like germanium silicon, there is a mismatch, but it's manageable. Silicon germanium or silicon, it's manageable. But there are combinations which the layer would simply crack if the mismatch is too high. So this one. Yes, you need to cross the critical thickness for these dislocations to form. But these half loops are mostly nucleating at some, let's say, defect sites or some roughness sites on the surface like this, and they nucleate as half loops, and only when they reach the interface, this misfit segment is the one that releases your strain, not the threading component. No, critical thickness is the thickness that you cross without any dislocation. It's pseudomorphic. Let's say if this is the thickness it has crossed. The moment it crosses, a half loop kind of nucleates on the surface. The glide plane is a plane where it does not take any energy to glide, almost no energy to glide down a closed packed plane, which is the 111 plane. It's highly atomically dense. All you need is switch of atomic bonds. So the moment it crosses, on the surface it nucleates and immediately almost it glides down the 111 plane and it reaches kind of the interface. It can also happen. So sometimes we see that there is a dislocation somewhere in the middle of a layer. It does not always have to like be at this interface. So somehow it formed and it kind of ended there. So even I would say when we are like bumping concentrations like this, you can typically think this to be also like a kind of homo interface. It can nucleate there as well.
So it's surfactant mediated epitaxy. Usually in an MBA community, they use it to glide those dislocation in different order on the surface. So yeah. in MOCVD or CVD, you guys also use
no surfactant. No? We use hydrogen. Hydrogen plays an analogous role to surfactants. So I did not go in details. One of the reason, okay, that is a different thing. How we stop this Stransky Krasnov island is to pump in a lot of hydrogen. Hydrogen when stays in the surface, atoms don't come and form those kind of pyramids or islands. They kind of stick to where they land and they get buried by the next growing layer. So hydrogen plays an analogous role to
that's
antimony.
That's about this, making this to be a layer. But I'm talking about, the people use this carbon, for example, there's a work from Georg Westens, so we have seen from Hanover. in mid 90s, they use the carbon to actually glide those dislocation along the plane, so that doesn't go up actually. So something like.
Now we don't use surfactants.
It's basically to glide those dislocation not across the layer, but along the plane.
Okay, we also need to think what dislocations were them. So if let's say the dislocation is a 90-degree mixed 90-degree or an edge dislocation. Here we have 60 degrees, so the Burgess vector makes an angle 60 degree. Its strain relieving component is proportional to cos 60. So it's much less than compared to a pure edge dislocation. If it's pure edge, it will glide naturally only along the interface medium. It will never thread up. Low merge dislocation. The mixed dislocation, there is always these threading arms. I mean, the gallium nitride picture that you showed, it was full of threading dislocation arms, right? Had it been pure edge dislocation, it would have only stayed in the surface. Those, you can make them glide and disappear at the edge of the crystal, something like that. So maybe that's something you tried, but I'll see what these people did with carbon as the surfactant.
Okay, so that's the liberty as a chairman I took. so let's thank the speaker once again.
Thank you. Thank you.
This was a wonderful talk, and also a lot of things we learned. Thank you for this.